Okay, so we're down to our last speaker of the day, and we have saved the best for last. We're talking about the Chief Data Officer of Certus Group, extremely conscientious guy, was formerly known as Geo Joe, and a little known fact, even though he lives in Florida, he still keeps his house at 83 degrees every single day of the year. Ladies and gentlemen, Mr. Joe Blankenship.
All right, let's go. So once again, my name is Joe Blankenship, CDO of Certus. I'm going to talk to you today about smart cities and the projects we did over on the American Victory ship. So we're going to go over the fundamentals of smart environments. Once again, the name smart cities is kind of deceiving, but I want to make sure we go over the basics of what a smart environment is, kind of go into a subclassification of smart maritime systems, and then kind of go into the case study on what we did on the American Victory ship in terms of building out our maritime lab. So what is a smart environment? Essentially, it's a collection of sensors that represents a space through collections of data and kind of storing that on several different types of computational elements. Now, once again, the key aspect of these environments is to make sure that you're capturing critical features of the physical and human spaces in a way that you want to quantify into a data format that then gets stored somewhere that helps guide some level of activity for decision making and some kind of metric for value of outcomes, both operationally and strategically within those environments. Now, the data collected from these sensors can be mobilized in any number of ways: simulations, automation, predictive modeling, and there are several different architectural forms that you can implement these in. From local to global, you have your smartphones, there are smart homes, smart buildings that have floor-to-floor integrations. Those constitute larger areas of smart cities. Smart ports are a part of that. So these things are becoming more and more interconnected, both in terms of devices and data, from cities to international. So it's a pretty exciting time to be looking at these kind of systems. These things are implemented in terms of just based on what kind of critical outcomes the stakeholders and people inside the environment want to elicit strategically and operationally. So from the physical aspects of the environment itself to the human places and activities going inside these physical environments to the cyber infrastructure and devices that kind of connect and overlap and collect on all those different processes and states that exist inside of a city, a home, etc. So the requirements that are constituted up front kind of drive how the smart environment kind of manifests over time. So everything from the sensors and the actuators that you select have to be scoped within what you want to collect inside that environment, and ultimately how you want to monitor things, and ultimately what you want to model based on the data that you get from these sensors all has to stem from a clear idea and guidance on what exactly you want your digital representation of that environment to be. Now, this all requires a lot of research and clear observation on exactly what is going on inside the environment, both from a physical and a human aspect, and then ultimately use that to drive good engineering decisions on exactly how you're going to build and deploy the smart environment over time. And in this case, scale really does matter. In terms of like a home, maybe not so much, maybe you have set activities, but as you scale up these things into bigger and bigger assemblages of both sensor and data, you have to take into account different kind of form factors, how they overlap with one each other inside of these larger data and system architectures, and ultimately how you're going to stage the deployments of these things to make sure that longitudinally the data you're collecting is going to represent the people and processes and ultimately the decisions you're going to be making with the data over time. And once again, there are a lot of considerations and challenges with deploying these systems. First is probably regulation. So regulation and policy, especially in the US, you have FCC in terms of the hardware considerations. You want to make sure that you're not flooding or overlapping with any already licensed or leased signals formats. And also you want to make sure that you're not conflicting with any other types of devices that aren't allowed to be in those kind of bands and spectrums. But probably more importantly than the hardware and the software aspect of this thing is the educational component of it. In a lot of these smart city scenarios, there are a lot of communities and population areas where people are apprehensive about being monitored 24/7 by smart city or smart environment infrastructure. This requires the people that want to deploy these kinds of systems to engage in a lot of outreach to ensure that people that are key stakeholders, people that are going to be your champions, community leaders, are going to be aware of the benefit to them of what these systems are going to be, what the ultimate value you're going to be eliciting for yourself, and how that is in their best interest to do so. Otherwise, you encounter stuff like digital divide and redlining, where communities end up getting kind of surveilled in their own like little technical panopticon. And you want to kind of avoid that because you run the risk of deploying a smart environment with the intention to collect a certain type of behavior or to optimize certain types of operations in that environment. But because of the manner that you deployed it, the people now act differently. They've changed their patterns of life. And now what you're collecting with that smart environment isn't at all what you intended to model up front. So making sure that those people have access to information, making sure they're part of the decision-making process for deploying that environment will help kind of avoid those kind of deterministic risks that you engage with when implementing these kind of systems at scale. So Certus did a lot of research up front to make sure that we kind of understood how to go about implementing these systems from scratch. And we looked at 2 cities in terms of their process in deploying kind of smart environments, smart city infrastructures. The first was the city of Pittsburgh. In the Allentown area of Pittsburgh, there was a free internet access Wi-Fi signal called PitMesh. It was deployed using Ubiquiti hardware, and it essentially allowed people that could not afford access or persistent access to internet to have free internet access for education, employment, and to provide other opportunities for them to get access to that. Over time, PitMesh evolved into a 501c3 nonprofit called MetaMesh, which is a wide area internet service provider service. So instead of just having free Wi-Fi, they now have very fast point-to-point internet, and they have made it to where you can apply for a system. They'll send you the commodity hardware to link up to their wide area internet service provider network, and then you have free internet like that. And it's now a service to the broader Pittsburgh area. So a very good success story there. Array of Things in Chicago was a bit different. That was a Waggle-based IoT infrastructure for doing mainly metropolitan environmental monitoring and research, mostly around meteorology and transportation. Now, that effort by the University of Chicago and with the city of Chicago was really good because they started out by taking that data directly from those devices with a little bit of ETL and then dumping it right onto the city's data portal. So everybody had access to that data. That later got superseded by Sage Continuum. So using the same Waggle architecture, they were able to mobilize a system format and a data format that cities all around the world could take, copy, and amend their own cities. So not only does Chicago now have a kind of improved standard for doing these kind of IoT projects, but cities all around the world can share the same type of data with the same formatting, kind of exchange those things in an international manner, which is really, really cool. But the key takeaway from both of these engagements was that, especially from MetaMesh, they were very clear that if you're going to be deploying a smart environment or doing anything with smart systems, period, that the people who these systems are going to be interacting with the most have to understand why it's in their space, why it benefits them, and ultimately what the data that is going to be collected there represents of them, so they don't feel threatened or feel prone to change their behaviors within those environments. So that brings us to smart maritime systems. So smart maritime systems, in our case, what we did with smart ports, we focused on the fact that these are environments that are meant to facilitate transportation from maritime land to maritime, and to accelerate maritime trade and commerce flows. You want to get the commodities out of the port, you want to get commodities into the port, you want to get them out of the port environment to go to whoever vendor is paying for that stuff, then vice versa. So there are a lot of major examples, and it is no surprise to anybody, port authorities aren't really keen on letting you just walk around a port and asking questions about how their stuff works. So a lot of this was done with gray literature and with whatever publications were done on these kind of environments. But from what we could tell, some of the leading examples like Port of Hamburg and Port of Antwerp are really focused on 2 major things, which was optimization of operations and management, and also energy efficiency. In fact, energy efficiency was kind of a trend along all smart ports because operating costs, fuel, energy, stuff like that, those are major impacts to their overall operational budget. So in a lot of cases, smart environments are A, cost savings measures, but B, also just process optimization standards. The Port of Qingdao in China, they specifically implemented their 5G system because of the flows going in and out of their ports were so voluminous that they really had to optimize operational speeds and acceleration with precision and accuracy to make sure they knew where every container was going into which ships so that ships don't get delayed out of port or coming into port. So not just energy efficiency, but obviously accelerating things as fast as possible to make sure they're maintaining optimal operational pace was critical. And going pretty, okay, we've got 10 minutes. So smart maritime environments, they're really cool interstitial smart environments because they kind of bridge maritime and they kind of go from the periphery of a smart city directly into a smart city. A lot of times urban environments kind of coincide with maritime environments, so there's a correlation there, but they don't have to. But when you're looking at smart maritime systems, you often are looking at smart city environments that overlap with it, as well as the transportation infrastructure. So there's at least 2 coinciding smart infrastructures that go with smart maritime systems. Now, once again, there's also the regulatory bridging that goes on there as well. You have different flagged ships from different nations. You have different policies in terms of what commodities go in and out of which ports, depending on what nations they are, where they're coming from, where they're going to. And then also have local law enforcement, Port Authority, DHS, stuff like that in the US. Like everybody has a certain legal purview, everybody has to observe certain practices inside these environments. So understanding that as part of your model, even though your model is mostly focused on monitor energy here, monitor person activity over here, monitor automation over here. What is going on with those processes matters to the people that want to mobilize the data coming off those systems to make decisions on what they're going to do, how they're going to do it, and who they have to report to in order to ensure that those things are done as securely as possible. So, but there's a lot of art of possible there. So when you're collecting and simulating these kind of environments, there's a lot of potential for automation, tracking of both the vessels, the commodities, the human labor assets going on there. But then, as I pointed out with all the examples, operations management and energy efficiency is also one of those things that's, it's cost effective, but also accelerates operational cost and produces more value for them over time. So pretty cool. But once again, there are a lot of challenges. To build up these smart port environments, they are extremely expensive, like very, very expensive. The examples in China and Europe, those were multi-million-dollar, sometimes reaching on billion-dollar processes. They had to spend a lot of money to get policy and regulations in place to allow for certain practices to occur, to enable the smart system deployments and installations in a way that was really secure and helped inform labor resources and people on the ground exactly how these environments were going to change around them and how that would affect them specifically, and how they then adjusted labor practices to accommodate those new systems. So pretty interesting stuff. So that brings us to Certus Group and what we did over in the channel side area with the American Victory ship. So the goal with that lab was to build an environment for smart maritime and smart port research. We needed something that was modular, could be adapted to a lot of different scenarios using very adaptable hardware and software solutions to make a system that was not just reproducible for any customer, but that could be trainable to a standard that they could then go and take that system and train other people with it. So it was a really interesting challenge, and we kind of had to focus in on the scale and the applicability of that system pretty quickly. So the first part of the solution was site selection. So the American Victory ship was a really good solution, even though I had some reservations about it initially. It was a really good solution for a lot of reasons. The first one is that if you're on top of a big ship and you have a telescopic mast, it gives you a lot of height and elevation right off the bat in the port environment, which means that your signal layer has a lot better line of sight with the devices that are going to be around you in that smart environment. So even though there's a lot of signal sinks and challenges there, you do have a lot of opportunity to put a lot of devices in a fairly high density to actually meet the simulations they'd be doing later. Another part of it is that it does give you a ship-to-port relationship to actually model inside of your systems as you're going along. So the ship, the internals of the ship, the deck itself, that can be replete with sensors. The port can have sensors, and then you can monitor the interactions between those. So that's another good one. Another aspect of it is that the Victory ship helped us understand how deploying things on a ship itself in terms of smart environment and smart maritime sensors themselves can be a challenge. So instead of going with a land-based system in the port environment around it, we chose to go with kind of one of the more difficult but more realistic deployment scenarios that might occur with these kind of systems. And then last but not least, deploying it in this environment allowed us to extend scale-based modeling. So you're on a ship that's in a port. That port is now extended into a smart city very close to it. So you get to do modeling that's based on those different scales of effect as well. So really, really cool conception, and did a lot of work to make sure that it was done correctly. Commercial off-the-shelf technology, that was another thing. We want to make sure that people could just have a phone or laptop, go anywhere and just start buying pieces of this model, put it together on their own, and then deploy scenarios and hardware that best matched their expectations for how they wanted to deploy a system of their own. So IoT devices of pretty standard formats, signals formats that could have those devices sit on those networks, and then making sure that these things could be deployed and function in a variety of different environments. Obviously, maritime environment being one of the more difficult for anything to work, but the other thing is getting good community partners. We did a lot of work up front to make sure that we worked with the American Victory ship and the Port Authority to make sure that everybody knew what was going on, make sure they know what we were doing when we're walking around looking like maniacs with radios and antennas and different stuff going on and off ship. They knew exactly who we are and what we were doing. We also had AWS, the resources our way, as well as the AbleNook team, who was responsible for helping us deploy the facility itself onto the ship. So a lot of good partners, a lot of good collaboration and communication between us, which made this thing go a lot smoother. Now, more about the Maritime Lab itself. AbleNook produces very cool modular facilities, and at first I was like, this is gonna be a headache. You know, it's like, I'm the kind of guy who just wants to throw a tent up there and just like, we'll just put radios around it and be fine. But the AbleNook presented an interesting scenario for me in terms of how would you deploy a system like this in a way that was secure, could be done across multiple sites, but then also allow the customer to adapt it to their needs. Like, it scale this thing up, scale this thing down without too much hassle, but still have something that looks like a proper lab, could allow people to work inside of it as a control and then deploy stuff out into the broader environment and still allow it to be adapted to whatever scenario they might come across. And AbleNook's modular facility model was just what we needed. You know, it adapted to deploying on the hatch. It allowed us to build it to specifications so that it blended right in with the ship. As you can see in that lower photo with the helicopter, I mean, it kind of was, we were able to build it to specification, just kind of blend right in with the ship, and it still had all the space and availability and functionality we needed to do all the lab-based stuff in and around the ship. So it ended up being a great choice. Now, once we had the facility on the ship, then we started building out the signals mesh and all the stuff that we need to put sensors on. So we went with a Wi-Fi mesh that also had LoRa gateways, 5G connectivity. We put it onto a telescopic mast and made sure that we had not just internet resources in terms of Starlink, LTE, and we also had a 5G LTE backup as well for internet. But we also made sure that we had cameras, microphones, plus stuff on top of the mast. And then we also, Tim Tuhel developed a tool called Munnel that allows us to remotely access this system from anywhere that has a Wi-Fi signal and do it in a secure manner. So, which is another key thing to these systems as well, is to allow remote access and remote monitoring for data analysis, modeling, et cetera. So, devices, this could be a whole talk unto itself. ESP32 devices, I love them. They come pretty much pre-made to be built to any kind of scenario. You can enter transducers to it and produce any number of sensors and actuators, literally dozens of them, depending on what scenario you want to. And as I mentioned, the mast comes equipped, or we equipped it with cameras, microphones, also a focused dish array for doing point-to-point and site-to-site connectivity, so you don't even need internet to do that. If you had an austere environment where you had no internet, you can obviously connect these things site-to-site and build your own mesh like that. So you can build it completely off the grid if you want to. The data architecture is very simple. We used AWS IoT for a lot of the stuff. However, we can deploy ChirpStack if you wanted to do an on-prem or hybrid deploy, and that integrates with AWS IoT, Things Network, any number of different IoT cloud resources. Also on site, Tim Tuhel developed a dashboard for doing low-code, no-code, so that you can take those IoT sensor data, represent them in dashboards, and then also use SKG and some of the data ETL tools on site to do all the processing you would need without having to go outside the site if you don't want to. So lessons learned, so I have like 50 seconds. Three main challenges that we kind of identified and would still like to work on as we go through this environment thing. One is scale the environment. Signals propagation and sensor density is always going to be a challenge in these environments. Once again, clear requirements up front, clear questions about what kind of environment you're building, what you want to monitor, and who the stakeholders are in terms of what value they want out of the environment, all kind of drive this. So if you know that, and you know that the sensor density has to be increased to accommodate stuff like steel reinforced concrete, a metal ship, fences, all the stuff that kind of sucks your signals down in the environment, you have to build to make sure you're compensating for all those challenges. The other one is the environmental constraints themselves. You don't really control the smart city so much as once you deploy your sensors, if something happens to the transportation infrastructure or happens to the buildings that you're monitoring, then you have to redeploy certain parts of the system. So persistent monitoring and adjustments to human-based behaviors as well is part of this whole development process. So as you go along, you have to essentially account for the fact that your system and the environment is going to change. And then last but not least, data volumes. These sensor arrays at volume and density produce a ton of data. So up front, you have to scope and model for the types of data and the dimensionality you're going to be getting off these sensors, and then make sure you have the compute and storage to match those requirements over time, because it will build up. So you need to make sure that if you're doing cloud, you have the budget. If you're doing on-prem, you have all the resources there to store it on-prem. And that is it. All right, thank you all much.